Hello, this is Professor Dan Kernler back with another video from Calc 3. We're moving on to section 17.2. We're going to do two videos in this section. This section is all about a new concept called a line integral. So this is going to connect to concepts you've done previously, actually similar to something in Calc 1, but of course we're going to be looking at it in 3 dimensions, so that adds some complexity. So we're going to define in this video, what a line integral is. And then we're going to evaluate some line integrals, and we're going to do the mass of a wire using a line integral. In the next video, we will address the next 3 objectives. So let's try to visualize, remind ourselves what these a single and double integral mean. So a single integral from Calc 1, you have some function of x, and you're going to integrate from a to b, and so you are finding the area under that curve. So it's a 2D area under the function f above a one-dimensional integral. Oops, for a double integral over some region R, we need 3 dimensions here. We have some function, that's a function of x and y, and there's some region in the plane, that's our region R. And then if we project that up to the surface, that did not look good. Let's try that again. Maybe all the way over to here, something like that, who knows? Projecting up. What we will get then is a volume. We get a 3D volume under the function above a 2-dimensional region. So that's the Calc 3 extension to that single integral from Calc 1. So what is a line integral? What we're going to do is we're going to have a function of 2 variables, a function of x and y, similar to the double integral, but we're going to integrate it over a curve. So I'm going to try to draw this for you. You can try to copy it in your notes, and then we will give you a maple visual of this. So again, there's some surface that's a function of x and y, and then there is a path in the xy plane. This is your path C, and that's in the xy plane. Not a region, but a path. And so instead of finding the area under a curve in 2 dimensions, like the single integral from Calc 1, or the volume under a surface, like in Calc 2, what we're going to do, or in Calc 3 here, what we did earlier in the course, what we're going to do is kind of project this path up to the surface, and then find the volume, or sorry, not the volume, find the area on that, kind of like a curtain, right? So we have like area under a curve, but the function is a 2-variable function. It's a multivariable function, and the area under it is the area like above a particular curve. So it's kind of an extension of both of the previous 2 combined. It's like a 2D curtain area, technically called a lateral surface area. Under the function f, so similar to the previous 2, above a curve C, given by, and we're gonna define our curves parametrically. As parametric curves x of t, y of t, and then t is going to go between some a and b. The way that we will derive this is below, but essentially what you're going to do here is imagine a small change in arc length here. Delta S, actually let's do that. Let's do that in a different color since we have the colors. So you have this delta S sub I, and then when I extend that up, I'm going to get a little rectangle there essentially, that the area, the A sub I, is the height at that particular X and Y, multiplied by that width, that delta S sub I, which is a little bit of arc length. And the arc length we should have it previous in our notes from section 14.4, that delta S sub I is the square root of the rate of change of X squared plus the rate of change of Y squared, which is essentially, times delta T, excuse me, which is essentially the magnitude of the derivative of R. And so looking down below here, moving on, and we're going to kind of go a little bit faster through this, but the idea is that if we add all of those up, we will get that area under the surface. Let me get to the next page in a bit, but let me hop over to Maple here. I have a visual that I'll link in the comments to one that's uploaded to the web, and you can play around with as well. But you can see here I have this curve, this black curve in the XY plane, and I have this function above it. The red is that curve kind of projected up to the function. And then if I let my t vary, I get like a surface, like a lateral surface. And so what a line integral is the area of that curtain. That's what a line integral is. I mean, there are some other meanings of it, but in this context, that's what that line integral means. Okay, so let's write the definition then on the next page and fill that in, and then we'll do a couple of examples. So here's a theorem about how to define this. The line integral is, go back to blue here, it is the integral from A to B of your function of, and then X and Y are parametrically defined in terms of t, and then the square root of this x prime of t squared plus y prime of t squared dt. And that square root of x prime of t, y prime of t that's the magnitude of our prime. So that's useful to kind of note that for future reference. Similarly, if we have R as a function of three variables, x and y and t, who are all x, y, t, all x, y, and z all depend on t, then you can do the same thing, would be the integral from a to b. Now those are t values, f of x of t, y of t, z of t, times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, all that dt. Okay. All right. So let's do an example. Evaluate this line integral of xy ds for the path given to the right. Well, one problem is we need R of t. We need it. We need the path. We need a parametric version of that path. The easiest version is simply to note that this is a line. You can see here it goes through the point 1, 5, and it goes through the origin. So y is equal to 5x. So the easiest parametric version then is to let R of t equal t and then 5t. That's the easiest version. Okay, 2, let's get the magnitude. Well, let's actually get R prime and then find its magnitude. R prime is easy here, 1 and 5. The magnitude of R prime will be the square root of 1 squared plus 5 squared, which will be the square root of 26. Okay, and then in our integral, if you look up above, we need f of x of t, y of t. Well, f of xy, the function of xy, equals x times y in this particular case. All right, that is our function, xy. And so that'll just be t times 5t. So in this case, that'll be 5t squared. I think we're almost ready. I think we're almost ready to set up the integral. That'll be the integral of 5t squared times the square root of 26 dt. And the last thing we have to figure out is the limits for t. But you can see here, the only way to start at 0, 0 is for t to be 0. And then the benefit of letting x be t is then the second point is when t is 1. So this is the integral from 0 to 1. And that is just a single variable integral from Calc 1. And that's what most of these are going to become. The challenge, like a lot of the things we've been doing, is setting up that integral. But it's just going to be an integral in terms of t. And so that's just 5 square root of 26 over 3 t cubed from 0 to 1. And so that's just 5/3 square root of 26. That is approximately, it's about 8.5 square units. Let me show you that one. I have a visual for that one in Maple as well. And so here is the region, and the red curtain is what we found the area of. You'll kind of see, you can kind of imagine if we look at it directly from the side, there's kind of like a little triangle there, right? So what if we found the area of that triangle and compared it to the line integral? So let's do that. The triangle area be 1/2 base times height. Let's see here. If we're looking at this in terms of, our curve above, we have 1, 5. So this is the base. That's 1/2. Base is square root of 26. And then the height will be the function value there, which will be, remember, that's the 0.15, and the function is x times y, and so that's 5. Whoops, times 5, right? The height is 5. So the height is 5. And that one is approximately, it's going to be bigger. It's about 12 3/4, about 12.75 square units. So you can see that does confirm what we suspect, that if we just kind of cut the corner there, then the triangle area is going to be bigger than what the actual line integral is. Okay, one more example in this video, and then we will call it a day. So one other application of a line integral is to imagine that you have a wire along your path. So your path here actually represents a wire. And you want to know the mass of the wire. And you can imagine a wire that actually isn't constant density. Its density varies along the wire. So what you can do then is you can imagine if I have a wire, there's some small delta S here. That mass, m sub I, would simply be the density at x sub I, y sub I times delta S, and the full mass would be to add those up along the curve, rho of xy ds, and that's exactly a line integral. So that's what we're going to do here for this one. We're going to find the mass of the wire by this curve, the following curve here, that's the curve below. And the density is pretty simple here. The density just increases as x increases. So it's kind of theoretical. There's 0 density over here. It becomes infinitely thin at the end. And then the density over here would be, over at the end, the density would be 1. So it increases in density as you move along. All right, let's take a look here. We need, I guess there's 2 different paths. Let's call them C1 and C2. It's not clear here. C1 is clearly a line. And I'm just going to give that one to you. I mean, that's 2x. C2, not quite so clear, but you can see it's plausible that it is a parabola. And let's actually treat it as a parabola, that y will be equal to 2x squared for that one. And that's, you'd have to be told that. You can't really assume that from the look of it, but you'd have to be told that. And we're going to be told that. So our mass will be the integral over C1 of the rho times ds plus the integral over C2 of the rho times ds. So let's look at C1. We have y is equal to 2x. So let's do our parametric equation, and we'll just have t and 2t. And so r prime will be 1, 2. The magnitude of r prime will be the square root of 5. And so the mass will be the integral of, oh, I have to have my function. My function is just x. So that'll just be t times the square root of 5 dt. And again, this one goes from 0 to 1. So that's square root of 5 halves t squared from 0 to 1. So that's square root of 5 halves for that one. And then for C2, y is equal to 2x squared. So the parametric version of that would be t and 2t squared. R prime here, a little more interesting. That would be the square root of 1 plus, oops, sorry, not doing them, just r prime. 1 and then 4t. So the magnitude of r prime would be the square root of 1 plus 16t squared. We'll call, I guess we should call the one above m1, call this one m2. That's the integral of, again, we're integrating x, so that's t. And then we have magnitude of r prime, 1 plus 16t squared dt. And again, we're going from 0 to 1. We won't always, but here the x value is 1. And so for these two examples, it has been 0 to 1. This one, hopefully you're recognizing how to do that one. That would be a simple u substitution. I'm kind of running out of space and time here. So I'm just going to say, it's an easy Calc 1 integral that I'm sure you can do. So this one ends up being 1/48 times 17 to the 3/2 minus 1. And so the total mass would be the square root of 5/2 plus 1/48 times 17 to the 3/2 minus 1. Okay. Whew, that is it for this video. The next video, we will look at an application involving force and work over an interval. And I think that's, yeah, and then there's one last example one last topic we'll do at the end of that video. But that is it for this first video in 17.2. We'll have another one coming up next.